Today, we're going to pull back the curtain on a concept that is quite literally the engine behind the most robust software on the planet, event-driven architecture, or EDA. It's the secret sauce that lets modern apps handle insane traffic spikes and, more importantly, stay online even when parts of them break. So, let's get into it.
So let's just start with a really critical question. Think about this for a second. In our super complex digital world, services fail. It's not a question of if, but when. But what if a single failure didn't have to trigger that catastrophic domino effect? What if your whole system was actually built to absorb those shocks and just keep on going? Well, that's the exact problem event-driven architecture was born to solve.
And to really get how it does that, we first have to look at how systems talk to each other. So over on the left, you've got the old-school synchronous model. Service A makes a direct call to B, who then calls C. See how they're all chained together? They're tightly coupled. If C is slow, guess what? Everybody waits. And if C fails, that whole chain can just snap. Now look to the right. This is the asynchronous, event-driven world. Services aren't talking directly to each other at all. Instead, they're all communicating through a central broker. They are, in a word, decoupled.
So here's what we've got on top. We're going to start by digging into why that old way just isn't cutting it anymore. Then, we'll meet the key players in an EDA ecosystem. After that, we'll see exactly how EDA helps you build systems that are both resilient and scalable. We'll look at a few common patterns, and then, and this is super important, we'll talk honestly about the trade-offs you have to make.
All right, let's jump into our first section. Why the old request-driven model is really starting to show its cracks. The fundamental issue boils down to one simple thing: the problem with waiting.
So in a synchronous system, when Service A needs something from Service B, it sends out a request, and then it just stops. It waits. It's blocked, totally unable to do anything else until it hears back. This direct dependency, this tight coupling, it's what creates bottlenecks and makes the whole system incredibly fragile. If Service B gets slow or goes down, Service A is immediately in trouble.
And that brings us right to the event-driven solution. Now, to understand it, we need to meet the core components, the key players that make this whole asynchronous world spin.
First up, we have the event producer. This is basically any part of your application that notices a change. Let's say a user places an order. The producer's one and only job is to announce that fact by publishing an event. And the really critical part is right there on the last line. It doesn't know or care who is listening. It essentially just shouts into the void, "Hey, an order was placed," and then it moves on with its life.
So, who's listening to that shout? Well, that's the job of the event broker. You can think of this as the central post office or the main switchboard for your entire system. This piece of middleware, things like Apache Kafka or RabbitMQ, is responsible for grabbing all those incoming events and making sure they get routed to the right destinations. It is the beating, decoupled heart of the whole architecture.
And where are those events going? To the event consumers, of course. These are the services that have basically raised their hand and said, "Hey, I'm really interested in order-placed events." So when the broker delivers that event to them, the consumer wakes up and does its job. Maybe it's updating the inventory or sending a confirmation email or telling the shipping department to get to work. And finally, we have to define the message itself, the event. Now this is a crucial distinction. An event is not a command. It is an immutable record, a statement of fact about something that has already happened. It's typically made up of two parts: a header, which has metadata like a timestamp, and then the payload, which carries the actual data about what changed.
Okay, so now that we know the players, let's see what they can actually do. This brings us to the twin pillars of event-driven architecture, how it helps us create systems that are both incredibly resilient and massively scalable.
The first pillar is resilience, and the secret sauce here is something we can call the buffer effect, which is all thanks to that central broker. It's all about how the system can handle failures gracefully without losing a single piece of data. Let me show you what I mean.
So, let's walk through a scenario. Imagine your email confirmation service, that's a consumer, crashes. It just goes offline. In a traditional system, this could cause the whole order placement process to fail. But not here. The producer just keeps on publishing order-placed events, totally unaware of the problem. The broker acts as a durable buffer, safely storing all those events. Then, when the email service gets fixed and comes back online, it simply asks the broker for everything it missed and starts working through the backlog. The result? Zero data loss. And the producer never even knew anything was wrong. Pretty cool, right?
All right, that's resilience. The second pillar is scalability. Because all these services are decoupled, you can scale them independently of one another. And this makes EDA absolutely brilliant for handling those sudden, massive spikes in traffic, like Black Friday.
So, imagine your order volume doesn't just double or triple, it suddenly multiplies by 10. A traditional, tightly coupled system would almost certainly buckle under that pressure. But an event-driven system? Well, it can handle this kind of spike with incredible elegance. Here's how. Just look at this comparison. On one side, you've got a single shipping service just getting hammered by a flood of order-placed events, is totally overwhelmed. With EDA, the solution is beautifully simple. You just spin up more instances of that specific service, maybe 9 more of them. The event broker sees these new workers come online and automatically starts distributing the load among all 10. You scale only the part of the system that's under stress, which is just ridiculously efficient.
Okay, so we've covered the theory. Now let's move on and look at a couple of common design patterns to see how these ideas are actually put into practice in the real world.
So, the most common pattern by far is called publish-subscribe, or pub-sub, and this really shows off the power of decoupling. A single event happens, let's say user signed up, and it gets published by one producer. But then, immediately and all at the same time, multiple different consumers react. The email service fires off a welcome message, the analytics service logs the sign-up for tracking, and the CRM service creates a brand new customer profile. The beauty is, the producer doesn't know about any of them. You can add a 4th or 5th consumer tomorrow without ever having to touch that original service.
Another really powerful pattern is event streaming. This is perfect for when you have these massive, high-speed data feeds. Think sensor data from IoT devices or tracking every single user click on a website. In this model, events are stored in an ordered, replayable log. This means not only can consumers process data in real time, but they can also go back in time to reprocess historical events, which is a total game changer for analytics or rebuilding system state.
Now, it's really important we have a balanced conversation here. All of this power and flexibility, well, it doesn't come for free. So for our final section, let's talk about the hidden trade-offs and the very real challenges that come with adopting EDA.
There are 3 big ones you absolutely have to be aware of. First, eventual consistency. Because everything is asynchronous, your data isn't instantly consistent across the whole system. There's a tiny delay as events propagate. Second, debugging gets way harder. Trying to trace one user's action as it flows through multiple decoupled services and queues. It's complex. You need specialized tools for that. And third, you have to design for something called idempotency. It's a fancy word, but it just means that your consumers have to be smart enough to handle getting the same message twice. So you don't, for example, accidentally charge a customer 2 times for the same order.
This table really sums up the whole conversation. When you compare it to a traditional REST-based architecture, EDA gives you incredibly low coupling, buffered recovery from failures, and that amazing ability to scale specific services. But the price you pay for all that is a big jump in overall system complexity. It's an incredibly powerful tool, but you have to wield it carefully.
So, we'll end with this question for you to think about. As our digital world gets more interconnected, more demanding, and way less tolerant to failure, the principles we've talked about, decoupling, resilience, scalability, they're not just nice-to-haves anymore. They're becoming essential. Event-driven architecture provides a blueprint for the future. The only question left is, are you building for it?